to the last of these three wonderful lectures that we've had from Senthil, and of course we'll thank him at the end, but let me thank him at the beginning of this last of the three for a great set of lectures and his visit here, which has been very fruitful, and we hope you will come back. And I especially want to acknowledge the Infosys Foundation for its grant, which has really made this visit. This is the first lecture series actually which kicks off that entire program, which has now become possible, and we hope to take that forward. And also, as I talk to you, request Senthil to let our friends know in the US and Europe and so on, Japan, that this is now possible. And especially want to acknowledge the support from Mrs. Murthy for this set of lectures, which we hope to take forward. Thank you.
Thank you, Sandeep, again for hosting me here, and thanks to this Infosys Foundation. I think it's wonderful that there is money for visitors and so on. All right, so I was going to start with what I finished with in the last lecture and make one comment that just reminded to make because of some discussion I had with Sandeep this morning. After discussing this boson, the speed integer quantum Hall state, I said that this, one way to think about what's going on is that if you think about the partition function of this model in the presence of background gauge field that couples to the global symmetry, and for greater generality, you are allowed to put yourself on some non-trivial space-time manifold, and you ask what the partition function looks like, that the non-trivialness of the SPT phase shows up as the phase of the partition function after you integrate out the dynamical degrees of freedom. And for this boson integer quantum Hall state, the induced effective action is this guy with, it's a Chern-Simons term with k even, and there's no gravitational Chern-Simons term and so on because there's no thermal Hall effect. So this point of view is very powerful from as a formal device to discuss and classify, in the right hands, classify these SPT phases. But if you're, depending on the question that you're asking and depending on what technology you're familiar with, it may not be the most useful thing to do, right? Even though formally it's correct, it may not be very, maybe very opaque on what the physics is. If it's just Chern-Simons that you induce, then you know the physics, you can just read it off. Chern-Simons is a familiar field theory. But in more complicated cases, or even in cases that are not complicated for other means of analysis, an example that I was giving Sandeep was if you have, say, a spin system in 2 dimensions with just Ising symmetry, right? And then you want to understand the SPT phases of this system. It's very easy to understand. They're very well understood from simple physics-based arguments. But to understand it from this point of view, where you now couple a background Z2 gauge field to the system, integrate it out, and ask what the phase of the partition function is. And to go from there to the physics, it's extremely complicated, right? And it wouldn't be a wrong thing to do, but for most physicists, it's not a fruitful thing to do, okay? So with that sort of comment, I want to move on.
Isn't the kind of thing Cyborg tried? Cyborg did do?
No, other people had done. For this discrete Z2 gauge field, I'm not aware that Cyborg has contributed to that effort.
Maybe it was, he once explained it to me maybe as an example for a simpler case or something else.
Right, so the thing that you may be remembering is, so I guess,
3-4 years ago.
Yeah, so 3-4 years ago, the thing you may be remembering is how to write an action for a Z2 gauge theory, right?
I remember you saying that the strongly coupling duality for the Ising model
Yeah.
is not correct unless you also couple one of the sides.
Oh yeah, sure. No, that's a simpler story. That's totally different. This 2 plus 1, you're talking about the duality of the 1 plus 1 de-Ising model, the Kramer's 1-year duality, right? And I'm aware of their story, which I, statmic people Yeah. In some form. But this one is about SPT phase in 2 plus 1 dimensions, right? So if you do the same thing for an SPT phase with Ising symmetry, you need some topological action for a Z2 gauge field in 2 dimensions, right? So how do you write that for a discrete gauge field? It's complicated, right? There's an answer that is known, but going from that known fancy looking answer to any physics is extremely complicated. While the physics is much more directly understood by many other methods of analysis, solvable models, field theory arguments, this and that, right? So the point I'm making is that the physics is a lot easier to understand in some cases than the formalism.
Since you brought this up, let me ask an embarrassing question. Why is the level K of the Chern-Simons theory the same as this, whatever it's called, Hall conductivity?
Okay, very good. All right, great question. Condensed matter for the talented string theorist. So we have the partition function in the presence of A and G, right? Now in general, the expectation value of the current is obtained by taking the derivative of the free energy with respect to the vector potential, right? So in this case, what we will get is that the average of J, right? We take the average of the action with respect to A, let's say Jx, Ax, right? And this gives me K over 2 pi d0 Ay minus dy A0, which is the current in the y direction, that's the electric field, the y direction. So that's the definition of the Hall conductivity. And we are working in units in which electric charge is 1 and h bar is 1. So really this is the same as K times E squared over h Ey, and that's the standard thing. Good. Keep these questions coming. I feel good. Whenever I can explain something I know well to, to anybody.
One more stupid question.
Yeah.
In what you were doing, it was important. It seemed important that you had a gap.
It is important, yeah.
However, you explained at some point that even if the boundary was not gapped, you could still meaningfully talk about.
That's right, yeah.
Partition function.
That's right.
Now, I want to know, is a similar statement true in the bulk? Suppose the bulk, we take the bulk gap to 0.
Mm-hmm.
The full partition function would be some crazy mess.
Right.
Is
Right.
it still true that somehow that the phase is well defined?
It could be, right? It depends on the system, I think. Just like for the boundary theory, the answer depends on which system you're talking about. For instance, there's many examples of 3 plus 1D anomalous theories which only occur at the boundary of 4 plus 1, and they may be gapless, right? So then what happens, the phase of the partition function of the 3 plus 1D gapless theory, right, is not quite gauge invariant, but it's cancelled by a bulk contribution, right? So sure. I suppose I didn't need to have gone to 3 plus 1. I could have just said this, and whatever I said earlier was about a 2 plus 1 dimensional theory.
But
right?
maybe
Gapless.
phase is not gauge invariant is well defined.
Exactly. Absolutely. That's right.
But is the phase itself some very complicated non-local thing?
For the particular example of this master's Dirac fermion, it's not, right? Yes. There one can just analyze it, and it's not.
Just show us, right?
That's right. It's this theta, whatever. Now, more generally, yeah, I don't know. It's a good question. I don't know. I mean, this is the one case where one can, you just work it out and you know the answer. Right?
But in that case, you sort of defined it also by taking a ratio, right? For with masses first.
No, that was in the bulk.
That was in the bulk.
So in the boundary, we just regularized the massless Dirac fermion with another massive Dirac fermion. right? You pick some regularization of the massless Dirac fermion, right? The simplest, physically most well-motivated thing is to pick a massive fermion, and then you calculate the phase of the partition function, and it's given by this number, which is some regulated sum over the sign of the eigenvalues of the Dirac operator.
Good, thank you. Yeah. But I'm just wondering whether, in general terms, at least if the representations are non-chiral but massless, that strategy could work. Because to the extent we're talking about regularizations, that would work out.
I think that it's basically a real thing, except for something else.
In 1 plus 1 dimensions, but if you're in 2 plus 1D or 3 plus 1D.
All I'm saying is you could make the question well posed at least, and
Right.
you get what you get.
Right. All right. Anyway, so with this caveat that I wanted to show this slide, but then, emphasize this caveat that even though one can and think about it along these lines, it's not clear that that is the best way to move forward in all cases. Right? It's nice, it's formal, and it's field theoretic, but maybe not useful. Okay, so now I want to give an example in 3 dimensions of non-trivial SPT phase of bosons. So let's study topological insulator of bosons now with both charge conservation and time reversal. Right? The same symmetries that protect topological insulators of the standard topological insulator of electrons. Okay? And in general, when you have these 2 symmetries, charge conservation and time reversal, so this is the U1 and this is an anti-unitary discrete symmetry, and you have to ask how time reversal interplays with the charge conservation. Right? Is electric charge even under time reversal or is it odd under time reversal? Right? And those are different groups. Right? So the simplest case, say if you had helium atoms, then the number of atoms is invariant is even under time reversal. Right? So let's pick that case where the boson charge is even under time reversal. Now, it's easy enough to analyze many other symmetry groups, including ones in which the boson charge is odd under time reversal. But let me just pick one concrete example. Okay? So this is the group U1 semi-direct time reversal. Okay? The semi-direct is because it's anti-unitary, so even though the boson charge is even, time reversal doesn't commute with the U1 gauge transformation because its time reversal is anti-unitary. Okay.
Sorry, I'm a little confused since experimentalist. I can read
But it's being recorded.
That's fine. But isn't the electric field, because it's gradient of the A0 component, and so on, isn't it odd in time reversal?
No, standard electric fields are even at a time reversal.
That's why I got confused. I say, all right, somehow it works out to be even.
I mean, A0 is even at a time reversal. Right? It's a
Oh, because minus I, there's some phase up there. Okay, yeah, sorry.
minus ID.
Yeah, okay, so normal electric charge would be even on the time.
Yeah, so that because electric charge is even, electric fields have to be even. Right? Gauss's law.
But you're saying you can have a situation where electric charge is odd.
Yeah, why not, right? So if my group is U1 cross time Z2T, right? So a good example will be, say, a spin model where I have a Z conservation, right? So let's say I take a model which is minus J perp Si plus Sj minus the Hermitian conjugate, right? So this model conserves Sz, right? Now Sz is the generator of U1 rotations, but under time reversal, spin is odd. So this is an example, right?
If you mean you can have a U1.
So there's clearly 2 different groups, U1 semi-direct time reversal and U1 direct time reversal. Right? And furthermore, bosons, we'll just take the simplest case. The bosons are Kramer singlets under time reversal. Yeah?
What distinction do these groups possess, like semi-direct and direct? What physics changes between
Right. So the electric charge is in this case, U1 semi-direct, the electric charge is even under time reversal. In this case, it's odd under time reversal, right? So some terms that you can add to the Hamiltonian in the first case will be prohibited in the second case, right? For instance, you can have a finite charge density in the ground state, and that will be compatible with time reversal. And you can have a chemical potential and so on. While here, a finite charge density is not compatible with time reversal. So there's clear differences, right? Okay, but let's just pick the simple and concrete example where the electric charge is even under time reversal.
Sorry, just
yeah.
one more. I was trying to generalize your argument to understand why thermal conductivity was the gravitational.
Right.
Was the gravitational.
Right. Right.
Can I think of it this way? Suppose I have a manifold with a circle.
Yeah.
Whose size is varying.
Okay.
Then the partition function on that manifold with a circle is a finite temperature partition function.
Right.
A circle.
Mm-hmm.
Because the size is varying, the temperature is varying. So I can think of that. So the change in the size of that circle would be the change in temperature.
Mm-hmm.
And then there will be a flux
right.
of T.
Right.
By differentiating the way you did it, that actually you would get it.
Yeah, I think that sounds right. I don't see why that would not work. The poor man's way of dealing with the gravitational Chern-Simons is to simply say that if you have gravitational Chern-Simons, that counts the chirality, the chiral central charge of the edge modes, right? The number of right movers minus number of left movers. That's precisely the, there's some convention defining the gravitational Chern-Simons term. I think the standard normalization is that if the coefficient is 1, that counts the number of Majorana modes. So twice the coefficient is the number of complex chiral modes, left mover minus right mover. And then a very elementary freshman physics type argument where you take two edges, raise the temperature on one edge compared to the other, will give you the thermal current.
Right, but
right.
Should be that there's some nice, beautiful argument like this one, right?
Yeah, this argument I gave you is beautiful. Anything that you do with freshman physics is beautiful. Beauty is in the eye of the beholder. You don't think about thermal circles and so on. That's more fancy, right? You have to go to grad school to understand that. Right? Okay. So I'm going to discuss the 3D boson topological insulators using physical arguments first, just to put Shiraz out of his comfort zone. And then, once I get him agitated enough, I will calm him down by giving the formal understanding. Okay. I mean, that's how we think about it. That's how Ashwin and I discussed it originally several years ago. So, okay. So the key aspects of the physics of this boson topological insulators in 3D with time reversal, that we'll find that just like the fermion topological insulator, there's again a quantized magnetoelectric effect. I think condensed matter physicists know what I mean when I say this. For the high energy people, this is the same as whether the axion angle is, whether there's a theta term or not. And for fermions, we saw that there's a theta term at theta equals pi. Now for bosons, the theta term will be at theta equals 2 pi. Okay? Associated with this, so all these things are associated with each other. We'll see that there are vortices at the surface that are fermions, which is very different from what an ordinary boson system will do, where the vortices of the boson field are bosons.
So the quantized in the first point was the same as that it was 2 pi rather than pi.
Sorry?
Is the word quantized there related to the fact that the theta angle was 2 pi?
No, it's not continuously tunable.
Okay.
Right? In the presence of time reversal, theta is fixed to be.
But it could have been pi.
No, pi is not time reversal invariant for bosons.
That's what I'm
So that I proved in my first lecture.
I'm very sorry, but I thought the normalization was such that for not because
you got this bound state which was automatically frozen.
Exactly, yeah. At theta equals pi, that was my homework problem for the experimentalists, to show that that was.
But just in terms of the normalization in the SF dual term, it was
Apparently, yeah, we'll come to that. We can discuss that at some length.
I should have already integrated your first lecture,
No, that's, we can discuss the normalization of the FF dual when we come to that part of the story, right? And we'll see that there is some exotic property of the bulk monopole of the external electromagnetic field, just like in the standard topological insulator, and we'll see exactly what it is. Now we can explicitly construct these boson topological insulators in a system of coupled layers by starting with a known phase in 2 space dimensions and stacking together, making a 3-dimensional system by stacking together an infinite number of layers of these, and then getting this system of coupled layers to undergo a phase transition from the set of decoupled 2D layers into a 3D phase. Right? So there's a construction which which tells you that all these things that we are going to discuss actually happens in some phase of matter. Okay, so if you start thinking about what a boson topological insulator might look like, right? For the fermion topological insulator, the characterization that's most useful from a practical point of view is what happens at the surface, right? And we know that there's an effective field theory for the surface for a fermionic topological band insulator, which is free fermions with an odd number of Dirac cones. And perhaps you have some interactions, but this is the basic story. Okay? So what is the analog of this state for a bosonic topological insulator? Right? So let's start by contemplating what a possible answer to that question might look like. Okay? So the key requirement of the surface theory, suppose there is a boson topological insulator, right? And it has some surface. What do we know about the surface? Right? What should we impose on the surface? Right? So key requirement is that a trivial symmetry preserving insulator is not possible at the surface. That it's not possible for the surface to be in a trivial gap state that preserves all the symmetries. Right? So that's the basic story. That's the basic requirement for something to be called a topological insulator. Okay?
explain this, but so when you said trivial, you mean the way it will be non-trivial is either the symmetry is broken,
Right.
or if it's preserved, you have some massless degrees of freedom or something.
Or it's gapped in there's some topological field theory at the boundary, but it's the topological field theory that cannot exist in lower dimension on its own.
Oh, okay.
Right.
You mean like you get the Chern-Simons, like we saw for the fermionic case, you get some Chern-Simons term with the wrong.
Exactly, that's right, yeah. But you can never get a completely trivial state, right? A completely trivial gap state with no weird response, nothing. That's just impossible. Right? An ordinary insulator is impossible. Right?
That's sort of the definition.
That's a key property of the topological insulator of fermions. And we want to ask whether there are bosonic states which have a similar non-trivial surface state, where the surface is guaranteed to be non-trivial. Okay? So there's a convenient implementation of this restriction through a dual point of view, where we think not in terms of the bosons, but in terms of topological defects of the bosons, which are vortices. Okay? Now, in 3 space dimensions, vortices are extended line-like objects. They are oriented loops. And if the bosons are formed as superfluid phase, then these vortices have a line tension. They cause huge energy. But we are interested in insulators of bosons. We have an insulator. You don't want the boson phase to be coherent across the entire sample. So the vortices must be quantum fluctuating all over the place. Right? The vortex loops must be swimming around freely in space.
Like a condensator
It's like a condensate of vortex loops, right?
That's why the phase is not coherent.
That's why the phase is not coherent. Okay. Now here we are interested in the surface. So in the bulk we have vortex loops that are doing all kinds of things. It's a quantum soup of these vortices. But at the surface, a vortex loop may try to penetrate the surface and go out into the external world. And at the point of penetration, there's point-like defects, and we want to say something about, so if you want to describe the surface in terms of vortices, we describe the surface in terms of these point-like objects where a bulk vortex line has intersected the surface. Okay. Okay. So let me review, or perhaps for some of you it's the first time you're seeing this, a very powerful point of view of a conventional system of two-dimensional bosons. Yeah.
So the vortex lines have to always go in perpendicular to this, like,
No.
can I then just simply define a 2D vortex on the surface theory?
Right, so that's what we're going to do. We're just going to define a 2D vortex on the surface theory, right? But it's important that the bulk is an insulator, right? Okay, so now we want to understand this 2D surface with a 3D topological insulator, but let's review what happens for an ordinary two-dimensional system of bosons, right? So there is a powerful point of view of conventional two-dimensional bosons, a powerful dual point of view in terms of vortex-like degrees of freedom. Now in two space dimensions, vortices are point defects. So the dual point of view is a description of the system in terms of point-like vortices. Okay. So there's a dual Lagrangian that one can think of as the Landau-Ginzburg theory for the quantum phases and phase transitions of a system of interacting bosons in two dimensions. And this dual Lagrangian is written in terms of a complex scalar field phi, which physically will identify with the bosonic vortex of with the vortex. It's a bosonic field, and it describes physically the vortex of in the phase of my original microscopic boson field. Okay, and in addition, there is a U1 gauge field, a mu, to which this vortex field is minimally coupled to. So this field phi is not gauge invariant. It couples to an internal dynamical U1 gauge field, a mu.
So the charge for a mu is vortex number.
The charge for a mu is vortex number, absolutely, that's right. Right? So vortex number is of course gauge invariant, but a vortex is also a physical object. Right? You can create vortices in a lab. In fact, they do it routinely in cold atom settings. People will take a cold atom Bose condensate, take a laser, stir it, and you'll see the vortices, right? Pratap creates them in a magnetic field. He doesn't do it with cold atoms. He does it with cold electrons, superconductors.
That's a good story.
Yeah, sorry?
Vortices in superconductors.
It's an old story. I'm saying all this only because I thought you might object to me talking about vortices. I have, but so if you don't object to it, let me just move on.
It exists as a solution of a Higgs field coupled to a gauge field.
Right. So here I'm talking about boson systems that microscopically are not coupled to any gauge fields. Right. So this vortex in a Bose condensed, in the superfluid phase, this vortex really causes logarithmic energy. And it's not something you can create locally. A superconductor is slightly different because the coupling to the dynamical gauge field, there's a screening, and then the vortex is really a point defect. It's something that can be created locally. Here, there's not local, it's not gauge invariant. But so long as we know what we're talking about, which we do, we are in good shape.
So just one question. So is it correct to say that in reality the vortices that we create at the interactions are non-local objects? And to
Yeah.
write them as point objects, you have to
Oh, absolutely. The physics is very simple. So maybe let me just explain the physical picture. So in the superfluid phase, right, so if you create a vortex, this is the standard thing that you would draw. The phase winds like that around the vortex, so this is a superflow. Right? We can think of this as the current flow or just what the phase of the order parameter is doing, and it's winding around all the way to infinity. Right? And that's what gives you this logarithmic energy cost, right, if you integrate the gradient squared of this phase. Now, in this dual description, we think about this instead as an electric charge, and think about these current lines as electric fields. So for every current line like this, you replace this guy by a line like that, right, which you can always do. So in this configuration, in terms of these dashed lines, it looks like these dashed lines are coming radially outwards. Right? So we associate these radially outward lines with the electric field lines, and then this is the electric charge and this is the electric field lines. So the point object that we are talking about is creating the electric charge without creating the electric field lines. And of course, that's not gauge invariant because it doesn't obey Gauss's law. But as a field in a Lagrangian, we are, of course, fields in the Lagrangian are not gauge invariant. Right? But we know that we have to impose Gauss's law, and then you create this guy, you create all this, and it's gauge invariant. Right? Okay. And in addition, so this is the vortex field, this is an internal gauge field. Now the physics of this internal gauge field is that its flux is precisely the physical boson current. Okay? So the external probe gauge field that couples to the global U1 current couples to the curl over 2 pi of little a. So in particular, the magnetic field, the dxay minus dyax divided by 2 pi of this internal gauge field is the physical boson density, while the electric field of this internal gauge field is the physical boson current rotated by 90 degrees. Okay? So that's the exact mapping. So there's an old duality. Actually, I guess my referencing here is a bit screwed up. I don't think these are the right years, but it's roughly around the right years. I think this was maybe 81 and this was maybe 79, but.
And how was this duality established?
What do you mean by established?
I was guessed.
No. So this lattice models in which you just derive, you know,
Is there an explicit change of variables?
it's an explicit change of variables on a lattice, right? So the real question to ask is, what does established mean? Because it's established at various levels of confidence, you know, and for what purpose, right? So there's a huge confusion, I think, amongst high energy instinct and condensed matter people on what the word duality means. Right? We mean not completely, fairly different things. Right? So the extent to which it was established in these papers is the following. Right? So in specific lattice models, you can do this explicit change of variables and so on. But then on universality grounds, we expect that the universal properties of the phase diagram are captured in both lattice models. Now, then there's a question of when can you take the continuum limit of both lattice models, right? And there it's not, the original lattice derivation will not tell you whether the continuum limit of both theories land in the same portion of the phase diagram, right? Or even land in the same portion of the phase boundary between, you know, where the theory is conformal. Right?
Let me understand that. Sorry. So you have two lattice models. There's just a change of variables which maps one to the other.
Right.
If so, the infrared
Should be the same.
unless what you're saying is I take some value of the coupling constant here, let's say weak coupling, it maps to say strong coupling,
Right.
and
Exactly, yeah.
I'm not sure whether
Exactly. That's exactly the point. So that the original lattice derivation will not tell you. And in particular, it could have happened that in this case,
There could be a phase transition where the lattice starts.
exactly. So, you know, so in this model, there's two prominent phases. There's this, that's indicated here, there's a superfluid phase, and then there is an insulator phase, a Mott insulator of bosons. Okay. So in terms of the original boson, physical boson description, you imagine this bosons in a periodic lattice with, say, on average, one boson per site. If the boson kinetic energy dominates, then the bosons basically Bose-condense and they form a superfluid phase. If the boson repulsion on every site dominates, then the bosons form an insulator. There's just one boson that's stuck at each site, so that's a Mott insulator. And there's a phase transition between the two. Okay. Now, in this vortex language, the way we describe that is to say that, so this theory also has two phases. I haven't told you what the Lagrangian is, but let's take some standard simple Lagrangian, 5 to 4. So then there's two phases. One phase is where phi is massive. So then you integrate it out to get a Maxwell action for a mu. Now, free Maxwell action, as all high energy people know, is dual to a free scalar. And that free scalar one identifies as the Goldstone mode of the superfluid. Right? And the gapped, and the phi field which was gapped is a gapped electric charge that couples to this Maxwell field as electric charge. So that's precisely the picture that I rubbed. So those are the vortex topological defects of the superfluid. Right?
So the last thing, the gap to electric exclusive, the last
Yeah. So the superfluid phase is, so this theory has one phase in which phi is massive. Let's just understand that phase. So when phi is massive, the deep IR physics is that of a free Maxwell theory, which is dual to a free scalar, and that's Goldstone physics. Right? We identify that with the Goldstone mode of the superfluid phase. And then the other excitation which we integrated out because it was massive, now let's bring that back in, that it has a gap, but it exists above the gap, and that's the electrically charged excitation. That's right. Now, if I create any such object, I have to create the electric field lines that come out of it. And we just saw that that maps precisely to the superfluid vortex. Those are the superfluid vortices. So the massive phase matches exactly the physical properties of a superfluid. Okay? And then, you know, if this Lagrangian is just phi to the 4, there's another phase, which is the Higgs phase of this theory, where phi has condensed. Right? And then the A mu field is Higgsed out, right? Anderson Higgsed out, right? It's gapped, right? And the Higgsing out of A mu means that the first, you know, this A mu used to be the Goldstone mode. Now there's no Goldstone mode, consistent with the fact that you've not broken the U1 symmetry, that it's an insulator, right? And second, that Higgsing quantizes the flux of A in units of 2 pi. That means the integral of this, there are quasi-particles in the system which are quantized flux tubes of this guy, where this integral over 2 pi is quantized to be an integer. Right? Now, those are precisely the physical original bosons, you know, the underlying bosonic particles in my system, which are well defined in a Mott insulator.
Which now have positive mass.
Which now gapped, they have positive mass, they're gapped, positive mass squared. They're gapped excitation in the system, and that's it.
N squared goes to minus N squared.
Exactly, that's right. Right? So,
Wait, so but just to understand, it seems to me that this lattice stuff that you're saying establishes the duality. If I'm interested in duality between the conformal field theories.
yeah, it doesn't do that.
Yeah, it establishes the same way as the lattice argument establishes confinement in QCD. It gives you a suggestion, but it doesn't quite establish it.
That's right, that's absolutely right. But what it does give is it's a suggestive argument in the following sense. It depends on what you mean by duality, right?
I'm interested only in duality in two conformal fields.
Right. So typically in condensed matter physics, that is also of interest, but we are interested in many other things, right? So the duality that was established in these earlier papers is enormously useful, mainly because, whether it's dual as conformal field theories or not, it's not that pertinent to many of the issues that we're actually interested in, right? In this case, it's to establish whether they are dual as conformal field theories can only be done numerically, and that has been done sometimes in the last 30-something years, and the numerical evidence looks quite good, right? So in other words, you take this theory, define it as a quantum field theory the way field theorists would, take phi to the 4 with a Maxwell term with some E squared and take the E squared to be much smaller than the coefficient of the phi to the 4 term. So that's a well-defined continuum field theory, simulate it, and then compare it with simulations of the 3D XY model and see whether the exponents and so on agree. That has been done and it seems to work, right?
So just to go back, there is a coupling constant in this theory, which is the charge of the boson.
Right.
I guess. And just to go back to what I was trying to say, if you do a map from the original theory to this vortex theory, is it that what is weakly coupled electric, which is a weakly coupled original
Right.
theory maps presumably to a strongly coupled?
That's right, yeah. So that's clear in the statement. It's the weak coupling limit of the original theory is the boson superfluid. Weak coupling meaning weak interactions, right? Weak interactions on a lattice, the kinetic energy dominates, that's the superfluid. But that's also the insulator of these bosons, which is where the boson potential energy, the vortex potential energy dominates over the vortex kinetic energy, right? So the real point is the following. So anytime we have two different lattice models that have the same phase diagram, right? We can identify both phase in both lattice models. Then it's natural to say that they both have the same properties at the phase boundary, that they have the same phase transition. That's an expectation based on universality. Now, it could have happened that this entire phase boundary is always second order, and every point on this phase boundary flows to the same, is described with the same fixed point, right? Which in this case would be a conformal field theory. Now, if we know that that is true, then we've got it established. Now, it could have happened, and this is actually a very likely scenario, not in this example, but in other cases, that one part of the phase boundary is second order, and then there's what's known as the tricritical point, and then there's another part of the phase boundary, right, which is first order. Okay. So then maybe in one formulation, one lattice model lands in this portion of the phase diagram, phase boundary. Another lattice model, when you tune it to its weak coupling limit, it lands in this portion of the phase boundary. In which case, what would happen is that as continuum field theories, one field theory flows to a conformal fixed point. The other field theory doesn't flow to a conformal field theory.
Or it could have happened that there was a line of Maslov, a line of.
Yes, so that kind of thing we usually can analyze. We will know if there's a line of fixed points. But the more serious problem, I don't think it's a problem, I think it's an exciting possibility. And I've asked many people over the years for examples of this phenomenon. And a lot of people tell me they know lots of examples, but they can't remember a single one. Your boss, for instance, is if there's again some tricritical point, some weird thing here, and this is also second order, but there are different fixed points that control these two portions of the phase boundary.
Two first order phase transitions.
No, two second order phase.
Sorry, two second order.
Everywhere on this phase boundary it's second order, but in one portion of the phase boundary, that second order transition is described by one fixed point, and here it's described by a completely different fixed point. Right? Two different CFTs that really separate appear as theories of critical points between the same two phases. So the phase is not different, but the critical points are different.
This is again another.
Right. So in clean systems, I don't know a single example. but I can't think of a reason why it's prohibited, right? Now, in random systems, there are many examples of this kind of thing.
Does there have to be a tri-critical point between these?
I don't know what to call this because
Does it have to have an extra relevant operator?
it does, right? Because, you know,
Because both of them are.
exactly, yeah. And perturbatively, it's very hard to see this. You need to have 3 zeros for the beta function to get this thing. So you have to do a very high loop calculation, right? So that's why I thought, you know, supersymmetric people and so on may probably know. But then I hear words like moduli space and I don't know what is going on. Anyway, if any of you know of an example, let me know. Because if this phenomenon could happen, then it could be that the weak coupling limit of both theories flows to conformal fixed points, but it's different conformal fixed points.
From the point of view of field theory, it's just that two lines of fixed points meet. It's
Two lines of, if it's lines of fixed points, yeah.
You want it to be the same fixed point at all.
Exactly, that's right, yeah. Then if it's a line of fixed points, what does it mean they meet?
Meaning you could have analytic behavior in this direction.
Yeah,
analytic behavior in
okay,
this direction.
yeah.
That is of course fair.
That one could imagine happening there.
Two-dimensional boson, the orbifold fixed points.
I don't know what orbifold is.
But
But there's some example there. Yeah.
Field theory is in 2 dimensions. This happens.
I see, okay.
Sure, there are many more like this, but there the theories vary.
The theory varies, all right, okay. Now that's still interesting, but the more dramatic phenomenon would be this guy, right? So I think in all these dualities, actually let me throw out the statement which I believe is correct. I think there are people in the field who believe a stronger statement. I think at small n, all these dualities in 2 plus 1D, non-supersymmetric dualities that we've all been discussing, not at large n, but at small n, we don't know to what extent they are really true as infrared dualities of the conformal field theory. We know that they are I'm totally confident that they are dualities in the same sense as the original Dasgupta-Halper and Peskin duality. And that's the level at which we need it for almost all of our condensed matter applications. So condensed matter people are very happy with just establishing it at that level, right? But if you really want to make a statement about dualities of CFTs, I don't think that's...
I didn't realize that your work doesn't give evidence that they are dualities of CFTs.
It gives evidence, but not proof.
Yeah.
It gives evidence just at this level.
I see, but no,
Right.
not some comparison with some experiment or something that doesn't give evidence.
All the Actually, let me also let you in on a secret. There's no comparison experiment so far. The experimental relevance of all the new things that we've been discussing is yet to happen.
But you can imagine an experiment that would establish that these are dualities of CFTs?
I can certainly imagine an experiment, but not an experiment that I can imagine anyone doing in.
Just to go back here, I'm still trying to process what you're saying. It seems to me that your usage of the word duality is a change of variables which allows you to solve the same model at 2 different values of coupling constant.
That's one
Because, as you said, I mean, after doing the duality, where you can actually analyze the theory
Yeah.
is in decoupling in the dual variable.
No. We can also analyze the theory in strong coupling in the dual variables because we are on a lattice, right? So we can do strong coupling expansions. You know, we have methods to deal with theories even at strong coupling because we are on a
So
lattice.
let me try to understand. So you have let's first work on the lattice. You have
Right.
a lattice model and you can solve it both at weak and strong coupling.
That's right, yeah.
Then you do a duality transformation which is an exact change of variables
Of a suitable model.
of a suitable model.
It won't be the exact model, but it will be a model that we expect will have the same universal properties.
Well, if it were an exact change of variables, then mathematics tells you that you get the same answers. Right?
Yes.
Okay. So then, of course, there's no issue. I mean, it's exactly the same model.
No, there's still an issue.
What's the issue?
So the issue is if you want to take away a lesson from this about the behavior of 2 different continuum field theories, right? So that, you know, so in the lattice, the space of the lattice coupling constants in which one theory has a good continuum limit may not be the same as the space of coupling constants.
Just a rewriting. You told me it's just a rewriting. So the continuum limit in the first description
Right.
can be converted into a limit in the second description.
But that may not be the limit in which the second description has its natural continuum field theory Lagrangian.
There could be two different limits.
Exactly, yeah.
All right, okay.
That's right.
Okay.
So there is a lattice model which may have two different continuum field theory descriptions. One of them is in terms of the same variables as the variables in terms of which the lattice model is formulated. The other is in terms of some weird variables that, you know, that are these vortex variables, blah, blah, blah.
Okay.
Right?
So you want to take two different limits of the same theory.
That's right.
And now you want to ask, are the two the same in these two limits? Okay, that may not be the case.
That may not be the case. But this kind of statement, where if the phase boundary is always described by the same fixed point, right? If we knew that, then we have more evidence that it works out. So, but the real sense in which when we talk about duality, sorry, yeah.
Can I still, sorry, but it's also interesting to take the same model and look at it both at strong and weak coupling. Right?
Sure, yeah, we know how to do that too.
Your original statement was that a given model at strong coupling might be a Mott insulator, at weak coupling might be
Right.
this, there might be a phase transition, right?
Right.
And in that case, literally the dual description would have the same behavior for sure because it's just
Absolutely, that's right, yeah,
theory.
that's right.
And you would have, if you have a fixed point in between, you'll have a fixed point in between.
That's right.
That's not the sense in which we think about the dualities we have been talking about.
I know.
Science theories, that they are weak and strong coupling descriptions of the same theory.
No, but a strong coupling description of lattice model is just not a continuum.
Exactly.
So that's why I asked him the question, but he said no, there are two, not only is there a continuum, there are two continuums, different ones.
Right. So somewhere in the, you know,
That's what I thought, that there's one continuum
so there's, let's say, a lattice model in terms of,
and the strong coupling.
there's a lattice xy model, let's say, in terms of some variables e to the I theta I, and their conjugate variables ni, right? So that's one description. And there's another description, and these are dual. So H in terms of some other variables e to the I phi I, and their conjugate variables n phi I, and some link variables aij and the corresponding electric fields eij, right? And this theory, think about an arbitrary Hamiltonian in the Hilbert space of this theory, which has some coupling constants ki, right? So then there's a map to some other coupling constants ki dual here, right? Now in some range of parameters of this, there's a natural continuum limit for this theory written directly in terms of a field psi, which is e to the I theta, and that will take the form of some phi 4 theory plus some potential v of psi squared, right? And then there's some other range of parameters of this theory where there's a natural continuum limit in terms of psi dual, which takes this form, psi vortex mod squared plus some potential v dual of mod psi v squared. Okay?
These two are not the same.
A priori, we don't know.
Weak coupling on the Ki side and weak coupling on the Ki side.
Exactly.
Yeah, that I agree. They won't be the same. Weak
That's
coupling
right.
on the Ki and weak coupling on the Ki dual side. But I'm just saying, if you were still interested in the question, what is happening to strong coupling on one side?
Strong lattice coupling. It's not a field theory.
Yeah, that's
Question.
strong coupling, which has nothing to do with field theory.
Exactly.
Well, in the field theory, you can move in coupling constant space.
But that's not the same as going to lattice shock.
The entire field theory works in the weak coupling limit of the lattice theory.
A continuum theory up onto the lattice.
So you can, but to get to the continuum theory, you have to take the lattice coupling to be.
Okay. But what I'm trying to say is, ultimately, from the continuum field theory point of view, you want to move in coupling constant space, right? You want to ask, do you have
Right.
phase transitions, and can you
Right. No, absolutely.
Ultimately, a question you
Good.
are trying to ask in the continuum field theory.
Good, good,
If
good.
you allow me to obtain a lattice version of continuum field theories, I will map that question to a lattice distribution.
No, good. So the issue is the following, right? It's it.
To understand this,
No. So the issue is exactly what I was drawing before. So in both theories, so in this formulation, you can hope that you see the phase transition from the superfluid to the Morton's leading phase, and that perhaps describes some portion of the phase boundary here, right? So this continuum theory perhaps describes this phase boundary somewhere here. And then it's a different continuum theory that you can write down. It describes the phase boundary somewhere there, right? Now, we don't know that all along this phase boundary, you have the same critical behavior, or even that it's critical. If we knew that, then we are in good shape, right? So it's what we call weak duality as opposed to strong duality, which
Let me just say one more thing in line with this. I mean, suppose you had phi I minus phi j. Sorry,
no.
We take phi I minus phi j square, which is like the analog of, with some gauge field, the
Yeah.
analog of the kinetic term
Right.
in lattice. Okay? You want to take the coupling to be some number divided by delta x
Yeah,
to go to the kinetic.
right.
And then you may want to take that number to be big or small. That's strong or weak coupling of the field there. But you must take delta x to 0.
That's right, yeah.
So the whole coefficient of the phi I minus phi j square must be going to infinity to get any field theory, irrespective of whether the field theory coupling is weak or strong.
Right.
But the duality takes the coefficient of phi I minus phi j square, which is weak, to the coefficient of phi I minus phi j square, which is small. So it's just not field theory, whether strong or weak. Maybe I'm saying something, repeating something.
Yeah, that's fine.
another continuum limit you
Right. So your statement is correct, but what he's saying is also correct, which is what he's trying to address here.
Yeah.
So strictly speaking, there is a weak coupling limit of this theory which works deep in the superfluid phase. But then this continuum theory we expect will also correctly describe this phase transition, right? And
I'm sorry, I understand what you're saying.
yeah,
Okay, so in case the nature of the phase transition
changes, then it may still, this duality as originally described will still be correct, but, sorry?
In describing deep into the phase.
In describing the phases, and it can also describe the question of whether the phase transition can be second order, it can answer universal questions about the phases and the phase diagram, but without it being dual as conformal field theories, right? So in some sense, this even though we call it weak duality, this is a much more versatile version. It's a much more powerful version of duality. And it even holds that this transition, in this example, we know that this transition is second order. At least it can be second order. But there's dualities in other models where the phase transition is always first order, right? But nevertheless, there is a dual description, right? So there's no conformal field theory anywhere in sight, but the notion of duality is still useful and powerful, okay? And in most condensed matter applications, that's the sense that really matters, right? It's a source of tremendous confusion in talking to high energy physicists. And I learned the real reason why from Cyborg. He tells me that in supersymmetric field theories, there are no first order transitions.
Outside of field theories, space of quantum field theories as defined by the renormalization group flows away from conformal field. So unless you start talking about conformal field theories, you don't know what you're talking about. That's how we do it.
Or free field theory, right? That, it may not be, yeah. But that's a very limited way to define field theory. So field theorists have a limited view of what field theory is. No, but also, Cyborg tells me that there's no first order phase transition in supersymmetric field theories. So he's never had to worry about this issue before. And condensed matter, and some of us, for some of these phase transitions, we've the main question that we keep getting asked is whether is this phase transition first order or second order. You know, that's some of the big issues in the field. So it would be wonderful for us to not worry about the possibility of a first order transition. But unfortunately, that's our life.
There are first order phase transitions in large atoms supersymmetry.
Aha. Okay. So he was wrong about that. I'm sure he knew. All right. There's all a major diversion, but that's all right. You know, it's a discussion that is worth having every time. But subject of, as I said, many confusions. But for our purpose, we don't care about the phase transition in this story. We only care about the ability to properly describe a system of interacting bosons with these dual variables, right?
And really sorry, but for this purpose of this discussion, from the underlying lattice point of view, we could say we have two different limits. In one limit, there's a continuum description
Right.
in terms of the original variables.
Right.
And the other in terms of what it's, and you therefore we can.
But both continuum theories are capable of describing both phases, and therefore should be capable of describing the phase transition, but maybe not necessarily the same portion of the phase diagram of the phase boundary, right? Okay. So the crucial point from this slide is that there's a very useful point of view of a standard trivial insulator of bosons as a condensate of vortices, right? So these two statements are the same statement. It's saying that the bosons have formed a trivial insulator and saying that the vortices in the boson field have condensed, right? So that's really what I need to run with the 3D boson topological insulator, okay? Okay, so now with that discussion of 2D bosons, let's return to the surface of 3D. Right? Now, what we want to do is to prohibit this trivial Mott insulator, which we saw is the same as a vortex condensate. Right? So, one way to prohibit it is to prevent the vortices from ever being able to condense. Right? If you want to demand that the surface of the 3D TI doesn't have a trivial insulator, we just demand that, look, vortices can never condense. Something happens to vortices that prevents the ability to condense. One way to implement this, it's a natural guess, is to say that maybe the vortices are fermions, because fermions can't condense. Right? No, remember, we're also dealing with time reversal, symmetric states. So in terms of statistics, these are the only two possibilities. Right? Okay, so that's what we'll do. We'll just explore this idea that if you just change the theory from the previous slide, which is standard 2D bosons with a bosonic vortex field, if you just change that to a fermion, then we are guaranteed that there's no trivial Mott insulator in the phase diagram. So maybe that's the right candidate for the surface of the 3D topological insulator. Okay? Sort of a common sense idea. Do you have a question?
So you said that time reversal symmetry means that what has to be either bosons or fermions, right?
Right.
But if you take a double Chern-Simons theory, that will have both anyons and time.
Right. So you could explore more complicated things like that, but you know, this is the simplest. And at the end of the day, we know that this is the only possibility. I mean, that there's a right answer for the surface, and B, this is the only possible answer. So that's it, right? So in principle, you're right. You could take any time reversal symmetric, you know, two-dimensional insulator with a global U1 symmetry and gauge that U1, and then produce superfluid, which is doing something. So in your example, that superfluid will also coexist with some weird topological order, right? So you know, that's a more exotic superfluid. You're building in more structure than is necessary. Okay, so now the way to proceed is quite simple. So let's pick some ordinary quantum field theory of fermions in two space dimensions with global U1 and time reversal symmetries. For instance, we'll take two massless Dirac cones, which can be regularized without any problem in 2 dimensions. We want to pick a non-anomalous theory, and then let's gauge the U1. Okay? Yeah?
Why having two massless Dirac cones important?
Right. If you have a single massless Dirac fermion, then there's a parity anomaly. So you can't regularize it while preserving time reversal in a strictly 2D system. Right? So we want to pick a non-anomalous theory and gauge it. Because it's precisely because eventually we want to gauge it, and if there's an anomaly, then gauging is a problem. So we don't want to do that. Right? So we'll pick some ordinary theory of fermions with global U1 and time reversal, and couple it to a U1 gauge field. So it's really the same Lagrangian as in the dual description of 2D bosons, except that the vortex field we now claim, we declare is a fermionic field. Okay? And I'll explain this comment in the next slide, that this theory has an anomalous implementation of the global symmetry, okay, or the physical global symmetry. And I'll explain this in the next few slides after that we can use it to describe a surface phase diagram. We can think of this as a Ginzburg-Landau theory for the surface of this 3D putative topological insulator.
At this stage, is this the only description of the surface?
No, there'll be many descriptions that you know, I'll give you several as we go along, right? But they all have the same anomaly. The only thing that we can guarantee is that they'll all have the same anomaly, right?
So you could describe that. So you've got some bosonic degrees on the surface.
Right.
Here you're trying to describe them in terms of the vortices.
That's right.
But you were also able to describe them directly in terms of the bosonic degrees.
You could, but it's directly in terms of the bosons. It's very complicated because the essential feature of the surface is that there's some obstruction to getting a totally trivial insulator, right? To build that directly in terms of the bosons is a bit complicated. We know how to do it, but in this case, the simplest description is to write it first, double the number of boson species, eventually let the bosons tunnel into each other. So just like I was doing in 2D previously. And then for this double boson theory, you write down some Lagrangian, but you introduce a theta term. And the role of this theta term is precisely to forbid a trivial gap phase at strong coupling. So it's not a very handleable point of view. We know that it's correct because we can map it to other things which we can analyze. But the vortex point of view, building in the obstruction to trivializing this boundary is trivial, and by focusing on the topological defect degrees of freedom. Okay? Okay, let me explain why this theory is anomalous. Before gauging, it's not anomalous, but after gauging, it's anomalous in the following precise sense. So remember, we are dealing with a system of bosons, right? So that's important to keep in mind. So let's think about a monopole configuration of the background gauge field A, right? 2 pi flux insertion of the background gauge field, right? When you do that, because of this mutual Chern-Simons looking term, such a background gauge flux carries internal gauge charge, little a charge of 1, right? To construct a gauge invariant monopole in capital A, you have to neutralize that by binding a C fermion, which also carries charge under U1 little a, which means the result is that the monopole in capital A is a fermion. Okay? Now that's okay if my underlying particles were fermions, but here my underlying particles are bosons, the same concept of underlying particles, which is really powerful to keep in mind, right? So this is not possible in any bosonic theory in strictly 2 dimensions. Okay? We'll see how this is resolved at the boundary of the 3D topological insulator. Right? It turns out that I'll give you the resolution. It turns out that the bulk magnetic monopole is also a fermion. So then when you tunnel a monopole from the vacuum into the bulk of the system by passing through the surface, the monopole statistics changes and it leaves behind, whatever it leaves behind at the surface is a fermion. That's the only way it's legal. I'll explain that as we go along. Okay? But this is why the theory is anomalous. It's anomalous as a bosonic theory. Okay?
Just to understand, this is by you're enforcing this, right? You're saying no exotic statistics can appear.
Exactly, yeah.
That's my definition of the kind of system I'm after.
My underlying system is bosonic, right?
Your underlying, but I thought, I see, and in 3 plus, and you're in 3 plus 1, so you don't
Right.
expect, you don't expect the exotic statistics to appear. So the underlying system is bosonic.
No, the microscopic degrees of freedom are bosonic.
Bosonic, so all excitations.
Right. So in particular, I mean, I guess this is the right.
But monopoles even in a bosonic system can have
No.
system that communicate from you.
Oh, but then the underlying physical system then is a fermion system.
No, I mean, you get a bound state of a monopole and an electron can become.
Oh, that's true, but I see.
A bound state of a monopole and a charge 1 object can become.
That's right. Yeah.
Because it can have angular momentum.
Exactly. Yeah. So exactly.
So that's why I'm asking.
We'll come to that, the bulk description in a minute, right? But here, suppose there is a strictly 2D bosonic system, right? Then I have vacuum here, right? It's embedded in 3-dimensional space. So then the monopole is a boson, the electromagnetic monopole is a boson here and here. Now let's imagine taking a monopole from here, throwing it from left to right, right? So it's a boson, and then it passes through and it comes here and it's still a boson, right? Here it can't nucleate a fermion, right? This process has to just nucleate a boson. That's it.
So you're saying the vacuum there is the topological insulator or actually the vacuum on your diagram in this?
No. So if this is an ordinary 2D theory, right? The monopole had better be the monopole insertion in this 2D theory had better be a boson.
Say if there's vacuum in 3 layers.
Sorry, let me just, by the vacuum you mean another theory, not the one you're considering?
Not the one I'm considering. I'm just taking an ordinary system of 2D bosons. I embedded it in ordinary 3-dimensional space. So everywhere in space, it's trivial. And my 2D system separates space into a right and a left. And I throw in a monopole from right to left. Right? Its statistics can't change. Right? But if one side is a topological insulator, statistics can change. Right? So that's the anomaly in this theory. Right? So let's look at the phase diagram. So if C is gapped, C is the vortex field, C is gapped, same argument as before, I get a free Maxwell action for little a. So that's dual to a Goldstone mode, so that's a superfluid. But the C field, the interpretation is that it's a vortex. So here my vortices have therefore become fermions. That's really the only difference in the superfluid phase. Right? In the condensed matter context, many people over the years, last 20, 25 years, every 5 years there's a paper saying, in this system of 2D bosons, because of some strong coupling effects, maybe the vortex has become a fermion. And then we'll do something with it. Right? Now what we now realize is that with time reversal, that's not possible in an ordinary 2D system. It's only possible at the boundary of some 3D thing. There's a caveat to that statement, which at least with ordinary realization of time reversal, there's a slight caveat which I can talk to people about at lunch, over lunch maybe. It has to do with this quantum realization of time reversal in these dualities.
And the whole point of this is that this is the only phase, right? That the C gap,
The C gaps.
There's no condensate.
There's no condensate. That's right. Now we could break time reversal in this theory by putting C in an integer quantum Hall state with sigma xy equals 1. Right? For instance, if this were 2 Dirac cones, imagine giving a mass gap to these Dirac fermions so as to induce a Chern-Simons term. for little a. Now that phase has a physical sigma xy, meaning a response for capital A, which has a sigma xy of 1 and a kappa xy, a thermal Hall conductivity of 0, meaning there is no induced gravitational Chern-Simons. Now for bosons, we already saw that sigma xy cannot be an odd integer in the absence of exotic excitations.
I didn't understand this. Phase 2, are you turning on a magnetic field that's outside?
Yeah, for instance, right? You break time reversal, or your magic system spontaneously breaks time reversal because of some interactions, right?
I thought you were turning on a magnetic field for little a. That was not true.
No, 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 no.
Because C couples to little a.
C couples little a, but then, you know, what I could have done is to imagine turning on some interactions. Concretely, let's say this theory of two Dirac fermions. Imagine coupling it to some scalar field, right? You know, and inducing some Gros-Neveu type phase transition where these fermions acquire a gap, right? In such a way that it breaks time reversal, right? So then, when I integrate out the fermions, I'll induce a Chern-Simons term for little a, and then if I integrate out little a, I'll induce a Chern-Simons term for capital A. I can work that through and see what the response is. And the claim is that I'll find that the response is that the induced Chern-Simons term for capital A will be a level 1 Chern-Simons term, and there's no gravitational Chern-Simons term. Now this is illegal in a strictly 2D system with no exotic excitations. We just saw that in the last lecture.
So level half for little a becomes level 1 for capital A?
Here there's two Dirac fermions.
So level
Right.
1 for little a.
Exactly, yeah. Right. So this thing is not legal in a strictly 2D system, but it's allowed at the boundary of a higher dimensional system. It's half of what's allowed for the boson integer quantum Hall effect in 2D. It's precisely half of that. Just like at the boundary of the electron topological insulator, you get sigma xy as half, which is half of what's allowed in 2D. Okay? Now the most interesting possibility is to recognize that even though fermions can't condense, pairs of fermions can condense, right? So let's condense pairs of fermions, right? So that's still a vortex condensate, and the phase is disordered, so it's an insulator. So it looks like I'm able to gap out the surface, right, and get a symmetry preserving gap state. But this insulator, I'll explain this in a minute. It's a gapped insulator, but it necessarily has fractional charge, and it's of a kind that's not allowed in a strictly 2D system. Let me explain this in a minute. You should tell me when to stop. I'll just keep talking while I say it.
Some very basic question.
Yeah.
Until you feel tired.
I will go on for like several hours.
I mean, so in the fermionic topological systems, what happened was you got a Chern-Simons term on the boundary with the wrong coefficient.
That's right. Here too, that's what we are getting. The coefficient is an odd integer instead of an even integer. And we know from yesterday that even integers what's legal for bosons.
I see. But the starting point, that is to say, the starting point you had was a perfectly normal 2D, 2 plus 1D
Field theory.
field theory.
Yes.
So why is it that
But with fermions.
but with fermions?
With fermionic fields in the Lagrangian,
With fermionic fields in the Lagrangian, which would have, I thought, risen in a 2 plus 1D world with no boundary, which was not the boundary.
exactly, but not in a system of bosons.
Yeah. There's no contradiction from that point of view because you're getting k equals 1.
Exactly, that's
So
right.
on a theory where if it's a 2 plus 1 directional theory, you can formulate fermions, you're allowed k because it has a space.
That's right.
So from that point of view, it's okay. But it's contradiction when you say, I thought it was only bosonic, so I should have been able to formulate it without a structure.
Exactly.
But this thing, such theories will not be valid descriptions of an underlying thing.
both of, so the crucial concept which the most powerful tool we have is to know what the underlying particles are. Okay, so let me explain this phase, what happens when we pair condensed C a bit more.
I would have then said that you're starting, so if you had a manifold 2 plus 1d1 which didn't have a spin structure,
Right.
you couldn't have written down LD.
I couldn't have written down?
Your starting point of a fermionic vortex field could not have been written down.
Why not?
Because I thought to...
Oh, then I had to take this A to be a spin C connection.
Okay. So,
Right. So I can formulate fermions up to 3 plus 1d. You can formulate them even on non-spin manifolds if I couple them to the spin C connection.
So what is the imprint in your starting point that the underlying degrees of freedom was on?
So all local operators in this theory are bosons. Okay? It's only the monopole in capital A where I'm doing something weird, right? I'm sort of changing, the monopole in capital A is not an internal sort of dynamical operator of the system, right? But all gauge invariant operators in this theory are bosons.
Yeah.
So
You should go on. But what I was trying to ask was that you had something I'm just trying to understand. Your starting point is an allowed starting point in any 2 plus 1d world.
right,
Even if that world did not allow a spring structure, I can have a spin C structure.
that's right, yeah,
And it's an allowed starting point.
that's right.
Then why is it that the end conclusion in terms of what you can get is not allowed in any purely 2 plus 1d world? This is what I'm trying to...
Oh, but that I just argued in terms of this monopole. I mean, by now I've given you, I guess, two different arguments, right? One is in terms of this monopole, and the other is in terms of what is in terms of the T broken surface state, which we see explicitly is illegal, right?
And even though it arose from an explicitly legal starting point.
No, in the earlier slide, I argued that the starting point is illegal, actually for precisely the same reason.
So maybe, sorry, I misunderstood that. So the
Yeah.
starting point was illegal because actually there's an anomaly in the gauge symmetry of A.
Of capital A.
Of capital.
And time reversal. It's this U1 semi-direct time reversal is realized anomalously.
Okay. And so
So let me maybe say one more thing. The problem is not with the Lagrangian itself. The problem is with the symmetry implementation. You know, this theory could have arisen in 2 dimensions without this this U capital A of 1 being a precise global symmetry. It could have been an emergent symmetry and then it's fine. But if it's a precise microscopic global symmetry, then there's a problem. Right? It's a symmetry implementation that's problematic. Just like in the boson integer quantum Hall state at the edge, we had a non-chiral theory. The theory itself is not problematic, but the symmetry implementation that only the right mover carries electric charge, that's what makes it anomalous.
So actually the symmetry for capital A is implemented anomalous.
Exactly, yeah.
And that's okay if this was a boundary
Of a 3 plus 1D SPT. Exactly. Right. Right, so now let's discuss the state. In some sense, this is the most interesting surface of this. These two are symmetry broken, right? So let's discuss the state. So this is the Lagrangian. Now, if you condense CC, since C is charge 1 under this U1 gauge field, condensing CC breaks UA of 1 to Z2, and you get a Z2 gauge theory. Okay. Now, in this state, the flux of little a is quantized. There's a charge 2 Higgs condensate for little a. So the flux of little a is quantized in units of pi, right? So this there are flux tubes where this integral is n over 2 with n being in Z. So, the elementary object is where the flux is pi, right. But this flux is precisely the physical capital A charge, flux by 2 pi is the capital A charge, which means that there are quasi-particles in this phase which have fractional charge of half. Okay. So, it is a phase with fractional, it is a gapped insulator, but it has fractional charge excitations. Okay. And then the unpaired C, the single C field, it now carries just a Z2 gate charge, right, and it survives as a gapped fermionic quasi-particle. So, I will call this guy, this first class of excitation with n equals 1, I will call that the M particle. And then there is another class of excitation which is the unpaired fermion, which I will call the epsilon particle, and this is electrically neutral, it has 0 UA1 charge, but this carries Z2 gauge charge under this internal unbroken Z2 subgroup of the gauged U1. And so, around this flux, this pi flux, it has a braiding phase of pi, as you expect in a Z2 gauge theory, right. So, this is a fractionalized phase where there is fractional quantum numbers and it is described by a Z2 gauge theory. Now, the fusion of M and epsilon, you take the M particle, the pi flux, and you bind it to it this epsilon particle. So, that fusion product is a boson. This is a boson, this is a fermion. So, the fusion you might have thought would be a fermion, but because of the mutual braiding, it is actually a boson. So, and this carries charge half, this carries charge 0, so this carries charge half. So, this is a charge half boson, and it is easy to check that this also has a pi braiding phase with either M or with epsilon. This really is just a Z2 gauge theory with 3 distinct topological quasi-particles. There is also the identity sector, so it is really 4 sectors, E, M and epsilon, and the E and M are both charge half bosons, and the epsilon, my arrow is sort of pointing the wrong place. I did not group it in keynote properly. The epsilon is a charge 0 fermion. Okay. So, this looks like a standard Z2 gauge theory. Young condensed matter physicists like to call a Z2 gauge theory the toric code. I don't know, are you young? No, okay. That proves that you are old.
Well, that's not even strictly correct, right? Because you don't turn on the Hamiltonian or the toric code, you don't have the electric field operator.
I don't have the electric field operator.
The old Z2 gauge
yeah.
had 2 terms.
Yeah, yeah.
It was the electric field.
That's right, yeah.
And the toric code, at least what Kitaya wrote down,
yeah.
doesn't have the electric field term, right? It has the magnetic field and the loosening of the gauge.
Exactly, yeah.
So
that's right.
Not even strictly true.
Perturbed toric code.
Sorry?
I don't know, everybody calls it the toric code. I try to tell people that they should just call it Z2 gauge theory. So I asked Kitaya why he called it the toric code. He said, oh, it's simple. It's a code and I put the model on its torus. Therefore, I called it the toric code.
It's not gauge theory. That part is because you loosen the gauge constraint.
Yeah. So there's a long debate on what is gauge theory, which is a separate debate. What is field theory? What is gauge theory? We'll eventually come up to what is string theory.
I'm just trying to get the phases.
Yeah.
So, if I take M around the E, I pick up a minus sign.
Right.
Similarly, E around, but E around the E
It's a boson.
is a boson, so I just pick up 1.
Exactly, yeah.
M around M
Is also a boson.
yes, but if I interchange, which of these 2 are fermions?
No, only epsilon is a fermion. So my arrow, let me just correct it in real time.
Right. Sorry.
So these are the correct arrows.
Sorry. Yeah. When I was saying E, I meant epsilon. Sorry. So I understand. I just want to understand that E is a boson.
Right. Very good.
Okay. So we get 1. If I interchange 2 E's, I get 1 minus sign because one of the influence include a fermion.
Right.
In addition, I get two factors of phase.
Right.
Should I think of this as rotation by pi for both of them and therefore adding up to minus sign?
You can think about it that way. That's right. That's exactly right. Yeah. So another way to think about it is E and M, you start with E and M, which are both bosons, but with the mutual braiding of pi. Now think about the bound state and just think about the spin of this particle.
Wait, sorry, you start with n and epsilon.
No, that's how I started, but you can start with anything, right? Start with E and M,
Yes.
form a bound state, and just think about the spin of this guy. Rotate by 2 pi, see what the phase changes. Rotate by 2 pi means you go around, so you pick up a phase minus 1. Right?
Slightly faster thread, but these magnetically charged particles are charged under capital A?
That's right. So when I say charge half, that refers to capital A charge.
And they have magnetic charge under the Z2.
That's right. Because once we specify this stuff and specify the braiding rules and fusion rules, we don't have to mention Z2 gauge theory anymore. Right? Specifying the topological data is all we need to do. Right? Now, this is an interesting surface. It's gapped. It's symmetry preserving. But it's topologically ordered. It's described by non-trivial TQFT on weird manifolds like ground state degeneracy, blah, blah, blah. But the most crucial thing is that the symmetry is realized in a manner that's prohibited in strict 2D. So this is an example of an anomalous topological quantum field theory. Okay? So if you want to write a Lagrangian for this TQFT, right? I just indicated that, but let me write it here. You'll write there's a standard Lagrangian for a Z2 gauge theory. As a mutual Chern-Simons theory, two-component Chern-Simons theory. So A1 dA2 over pi. Okay? So this is the Lagrangian for a Z2 gauge theory. Okay? No. So this is a topological field theory. Right? So this theory has various operators, right, which there's a flux of, there's a monopole operator in A1, monopole operator in A2, which correspond to the E and M particles, right, and they have this mutual braiding phase of pi. Now the statement here is that E and M both carry charge half under U1, which means that the external gauge field couples to dA1 plus dA2 over pi, over 2 pi. Okay? So this is the TQFT, and this is problematic with time reversal. Right? If you integrate out A1 and A2, you'll find that it induces a Chern-Simons term for capital A. So that it has a Hall conductivity of 1, which is not legal with time reversal. So this symmetry implementation, so the topological field theory is a perfectly reasonable 2D topological field theory. But it's the symmetry implementation that is problematic. It's anomalous. So you have to do something to, it's not realizable in any strictly 2D system. Okay? So in fact, this kind of state turns out to be very powerful as a non-perturbative characterization of a topological insulator. Right? Because it's not a weak coupling description. It's and understanding the anomaly in the gapped boundary of a topological insulator has been extremely useful. That was one of our main devices in what we eventually did with fermions and classifying electronic DIs in the Z2 cubed. So you asked how those results were derived. We targeted states like these, right? And that's also why I didn't want to explain it before it explained things like this.
And when you say understanding the anomaly, it's understanding the effective action for the capital.
Oh, not action. It's actually most convenient not to try to write an action, but just to give the topological data, the braiding, fusion rules, and the symmetry transformations.
But isn't that in the end, the anomaly was captured by a partition function for capital, right?
In this simple example,
yes.
Right? Now, there are more and more complicated examples. Once you go even to the standard electronic topological insulator, In free fermion theory, it's gapless, and the gaplessness is protected by time reversal. Now, with strong interactions, you can gap it out, but then it will be topologically ordered. But the gapped topologically ordered state, unlike in this case where it's an abelian topological order, turns out to be non-abelian, and it's quite complicated. Right? And writing down an action is sort of a complicated thing to do if you have a non-abelian topological order. But we know the topological data. The fusion and braiding rules are consistent with the U1 and time reversal symmetries, but the actual symmetry implementation is not.
I'm really sorry to be asking this again and again, but when we say the symmetry implementation is anomalous, let me just try to understand. In terms of capital A, if
Yeah.
you integrate out everything else, you get a Chern-Simons term.
Right.
That has a coefficient
Right.
which is not allowed by gauge invariance if you say that the underlying charges are quantized the way they are. Is that what you meant?
No, in this case, the fact that you get in a here, remember this phase preserves all the symmetries.
Space, you mean?
This phase
For the phase, yeah.
preserves all the symmetries. So you're not supposed to be able to get a Hall conductivity, an induced Chern-Simons term in a time reversal symmetric phase.
Okay.
Right? So, which means that, so let me complete the story then. So this is just the description of this TQFT, and this is the charge assignment. But when we integrate it out, we get a Chern-Simons term for this guy with level 1, which is the wrong level. Right? So this theory is not really time reversal invariant as it stands. Now, there is a way to make it time reversal invariant, which is to just add a contact term for the background gauge field. So we just, in this case, just add this guy.
To cancel what you would
To
get.
cancel, exactly.
Fine, yeah.
And this only depends on the background gauge field, not on the dynamical degrees of freedom. But this thing that I've added is not legal for a boson system, unless it's at the boundary of a topological insulator. So you were asking me 2 days back about contact terms. It's sort of totally trivial.
It's not legal for a boson system because the bosonic system would have a charge such that 1/4 pi is not the right.
Exactly, it has to be even.
It has to be. That's what.
Right? So the
That's connected to what the underlying degrees of freedom.
everything goes back to what the underlying degrees of freedom are.
So you would have got an A wedge dA. First of all, I see the argument is more complicated than just saying you get an A wedge dA of the wrong coefficient. You say the fact that you get it at all.
You get it at all means that there's a problem. You can cancel it with a term that only depends on the background gauge field. But then what you have to add to cancel it is not a legal thing by itself in a boson system. In a 2D boson system, but at the boundary of 3D, it's okay.
Do you know enough about the surface theory to say that what you got in the first place was the first 2 lines without the last? Otherwise, maybe what you get is the whole thing together.
No, what you do get is the whole thing together because I'm living at the boundary of the 3D topological insulator. But in a strictly 2D system with this topological data and this charge assignment, I'm not allowed to get this extra guy. I'm only allowed to get this. And then the phase exists, but it will not be time reversal invariant. Okay.
Is there a way to see that you aren't allowed this charge assignment without using the Chern-Simons terms? Or is it
Yeah. So there is a way to see it by doing the monopole argument too. It's actually very nice to see it that way. It's very physical. So imagine you again through this monopole from the vacuum inside, inserted a monopole into this system, right? And so as the monopole goes through, you change the electromagnetic flux by 2 pi. Now any object that carries charge half, when it goes around it, it will pick up around 2 pi flux, it will pick up a phase of -1. But really, you want a 2 pi flux insertion to be a local process. It shouldn't be detectable by quasi-particles far away, which means that you have to hide this Aharonov-Bohm phase by nucleating some other quasi-particle. In this case, you have to nucleate the neutral epsilon particle, right, with which the other guys have braiding statistics of -1. So again, you see that the monopole is a fermion, which it's not allowed to be in a strictly 2D world. So that's a way to see it without writing down a Lagrangian.
And of course, it's important to have A as an ordinary connection, not
A is an ordinary connection, that's right, because A is couples to bosons. So that's the, again, underlying particle is a boson. Okay. Yeah, I just wanted to keep emphasizing this because this has been a very powerful tool to think about the strongly interacting topological, SPT phases. But it does fail sometimes because there are some classes of SPT phase in 3+1 dimensions for which there is no such symmetric gap surface. And the surface either breaks the symmetry or is necessarily gapless. For those, we need different tools. But where it works, it's extremely powerful. Okay? All right. So far, I sort of waved my hands, I made guesses, and I got the theory of the surface, and it made sense. Right? So now let's see what it implies for the bulk, and let's try and characterize. That's the logical progression, right? We want to understand the surface, but ultimately we want to understand it without any surface. What's non-trivial in the bulk, right? And so to understand what might happen in the bulk, let's couple the global U1 to a background gauge field and integrate out the bosons. For the electron Ti, we know that there is a theta term at theta equals pi. Now for the boson Ti, the claim is that theta is 2 pi. Okay? And the simplest way to argue this is from the time reversal broken surface state, which has sigma xy equals 1 and kappa xy equals 0. So the Chern-Simons term that you induce at the surface is half, it's twice what you get for the electron Ti, and therefore the bulk theta term will be twice what you get. Now we can also ask with this theta equals 2 pi what the fate of the bulk monopole is. Now the Witten effect tells you that the bulk monopole will carry an electric charge of theta over 2 pi plus an integer, but theta is 2 pi, so the monopole only carries integer charge, right? So there's no fractional charge on a magnetic monopole, unlike in the electronic topological insulator. But here what happens is that the new feature is that there is an electrically neutral monopole, but that monopole is now a fermion. So there's a nice picture if you draw the lattice of allowed charge and allowed monopoles, right? In the theory at theta equals 0, you have a square lattice. Now measure this in units so that Dirac quantization is satisfied. And this is a boson by definition. That's the basic electric charge. Now in the ordinary insulator, the basic monopole is also a boson. But in the dion, which is the bound state, which is precisely what we were talking about, this is a fermion, right? So now at theta equals 2 pi, as I change theta, this thing shifts 1 over to the right, right? And then, so at theta equals 2 pi, this picture changes. The neutral guy now becomes a fermion, right? So this is a fermion, this is a boson, and this is a boson, right? And this fact that the neutral monopole has become a fermion is closely related to the fact that the surface vortex is a fermion. Because the way to create a vortex on the surface is to throw a monopole from bulk to surface, from vacuum to the interior. Here the monopole is a boson, here the monopole is a fermion. So what it leaves behind at the surface is a fermion. So that's basically the reason why our original guess basically works. Right? And this gives you a sharp bulk distinction from the trivial boson insulator, just like the fractional charge on the monopole did for the.
Which is whether the neutral monopole is bosonic or not.
Exactly. So, and this distinction is sharp only in the presence of time reversal. In the absence of time reversal, it can continuously tune theta and change the statistics. Okay? Yeah.
Observing any of this, would that involve things like what, I mean, how would you observe any interference experiments?
Like observe which aspect of the
Let's say
stuff?
that the vortex is a fermion.
Oh, yeah, perhaps the simplest would be to try to get into this quantum Hall state and measure the sigma xy. That's right. Break time reversal, deposit a ferromagnet at the surface. Actually, the right experiment would be to deposit a ferromagnet at the surface, form a domain wall, and then look at the edge state. And the edge state will be non-chiral, but only one guy will transport charge, just like the edge of the 2D boson integer quantum Hall state. Okay, so finally, let me come to the formal description. Thought Shiraz would be very agitated, but he's very calm. So maybe I don't need to write this, but let me do it anyway. So let's ask about the formal description in the bulk, right? So where we take our bulk partition function in the presence of a background gauge field and background metric, and restrict for simplicity to oriented compact manifolds, right? So then there's some partition function, and we imagine integrating out the bosons, and there'll be some modulus to this partition function which we don't care about, and then there's a phase which involves this theta term, right? And with theta equals 2 pi, the claim is that if the boson is in a topological insulator, then this theta equals 2 pi, okay? And that theta equals 2 pi for bosons is both time reversal invariant and non-trivial. And that for bosons, the physics is periodic under 4 pi shifts of theta rather than 2 pi shifts of theta. Okay? And there is no gravitational or wedge odd term, at least for the particular boson topological insulator that I am describing. There is another boson topological insulator for which there is no wedge odd term.
The physics is different at theta equals 2 pi precisely because monopoles are
of fermions. The neutral monopoles of fermions.
The spectrum, if you don't look at where the boson or fermion is the same.
Exactly, that's right.
But can I ask something? This monopole is a monopole in the background gauge field.
That's right, yeah.
We're not sure if it's a physical excitation.
It's not a physical excitation of the original system. Just like the charge E over 2 monopole in the standard topological insulator, the only reason it's allowed to exist is because it's not a dynamical excitation, it's a property of a probe where you change the Hamiltonian of the system.
So, I mean, if I just had a bulk insulator with no boundaries, first of all, is there any dependence on theta at all? You say it depends on whether I can introduce this external probe.
Exactly. So if you don't introduce any external dynamical charges, then it's hard to know, right?
So you have to introduce this monopole to see
Yeah.
the charge of the
Right. You could see it if you put the theory on weird manifolds. If it's a non-spin manifold and then there's some W2, there's some obstruction defining spin structure, and then you ask what's the quantization of the flux, whether it's multiple of 2 pi or shifted from 2 pi by a half. So that will be a way to tell whether the original particle is, whether it's a spin C connection or U1 gauge field. But those are complicated things. Just look at the monopole. So this, it's because we were always looking at these gapped excitations and using that to characterize the phase that we managed to get away without knowing a thing about spin structure or spin C or anything, right? It's only if you want to throw away all these gap things and just focus on the deep IR that you need these more sophisticated things.
And the last thing is, therefore, I mean, an experimentalist who doesn't have access to this probe monopole probably has to look at a boundary.
Yeah, that's right.
And then you do this.
That's right.
Wasn't
The same is true for the electron topological insulator, right? We don't have access to monopoles. If we did, that would be the cleanest probe without having to look at the boundary. But boundaries anyway exist in the real world, so it's very convenient. Anyway, so the completion of this story of the boson topological insulator is that knowledgeable people would have told us the answer right away.
This is just the dual of the statement you made for the Chern science.
Exactly. It's the one dimension higher version of the statement. It's a reduction to the boundary, exactly. So if you knew about how instanton numbers for a U1 gauge field is quantized on a non-spin manifold, then you know that this thing is quantized in such a way that this 4 pi periodicity, and
So integral 1/8 pi square f wedge f on a non-spin manifold
is quantized
as 4 pi, as whatever, 1/4 pi n, whatever it is, I mean,
half integer. That's right. So the periodicity occurs only after you shift by 4 pi. I even know how to prove this statement by now. You start with the standard index theorem for the spin C connection, and then you play around with it. You can prove all these statements using index theorems, right? But I personally feel that a lot of people knew these statements for a long time, for like 30 years, maybe even longer, right? And a lot of people also knew that theta equals pi for the electron for fermions, right? That for spin C connection, knew the index theorem for a spin C connection for, I don't know, decades, right? But topological insulators didn't exist, even in theory space, till the last 10 years. It's knowing the math fact. It's been much more useful after we've understood things to connect it to some formal math structure than no one who knew the maths understood the physics. But once we understand it, it's nice to connect it with this formal math stuff. Want me to go on, or I can stop? Whatever you deem fit. I can stop any time. I mean, this is as natural a stopping point as anything else that I would say. Now, what was in my slides? I'm just going to give you some feeling for how we proved the Z2 cube thing, if you care, but
Yeah,
I'm happy to.
Just a sense for you.
Yeah, I can do that. That's very easy. So now we have all the tools, right? This boson topological insulator is a stepping stone, really. So the idea is the following. So Z2 cube means there are 3 generators, right? So to remind you, not talking about electronic topological insulators with U1 semi-direct time reversal symmetry where electrons are Cramer's doublets under time reversal. Okay. So what are these 3 root phases? One of them is this familiar topological band insulator. And there's 2 others which are the electronic Mott insulators where the spins have formed a spin spt. So these topological paramagnets. Okay. So we already saw that time reversal symmetric insulators with no exotic excitations for fermions, the electric charge is for the monopole is either 0 or E/2. Okay. So that's one constraint on any possible such time reversal symmetric electronic insulator, right?
That's theta equals 0 or pi.
Theta equals 0 or pi. Now, there's a highly non-trivial statement that we proved that monopoles in such insulators must always be bosons. so this is a very complicated proof. It was the hardest thing we had to do. I don't understand it from a formal point of view, but humankind does. Witten knew our paper, and last time I saw him, he told me that he has a formal understanding of this statement, and that this is the boundary of a 4+1D theory with a W2, W3 anomaly. He explained it to me, gave a beautiful lecture. So W2 is the second Stiefel-Whitney class in oriented manifold. It's the obstruction to having spin structure, and W3 in 5 dimensions is the obstruction to having spin C structure. Now, for such a 5D state, this is the boundary, and so there's an anomaly, right? So we gave a poor man's proof, which was, given what we knew, that's what we could do. But I'm glad that the statement survives scrutiny by experts. So let's assume this statement, right? So then we know 2 things about the monopole: that it must either have one of these 2 charges, or it must be a boson, right? So the question is, what other possibilities exist other than the 2 conventional band insulators, right? Now, the first statement is that because these SPT phases have a group structure, you can stack them to produce other ones.
Sorry, what is the angular momentum of one of these E/2?
Angular momentum? What do you mean by angular momentum? Under what?
Just E cross B angular momentum.
E cross B angular momentum. So that will determine the statistics, right?
So you're saying that
that's a boson. That's bosonic, right? It's integer angular momentum.
What's puzzling me is this: that if we just had, sorry, it's a stupid way, but if we just had a unit charge monopole and a unit charge electron,
right?
That angular momentum would be half.
Exactly, yeah.
Now,
that's
why
right.
do you think this was 1/4?
Yeah, okay. So this is yeah, I don't know how that works out, but this charge, it's some polarization of the medium, right? Certainly it contributes to the, turning on this theta term in any theory doesn't change the statistics, right? It's polarization of the medium as opposed to.
So it's the charge before you do this theta shift.
Exactly.
That's why it was.
Exactly. That's right. Yeah.
I mean, imagine what the spectrum was before you did this theta shift. Then it's just a monopole with no electron charge. Then clearly this E cross beta was just 0.
Exactly. And then you're polarizing the medium, right?
Doesn't change.
You're not binding a particle, you're just polarizing the medium.
So theta also somehow contributes to
Exactly. That must be what it is. Yeah. Or the definition of angular momentum has changed, right? Okay. Because these SPT phases have a group structure, a abelian group structure, you can add together 2 SPT phases and get a third one.
So, but is this statement itself just a proof for the monopoles or the bosons?
No. So the question is whether there's some non-trivial SPT state, or more generally, suppose is there a U1 gauge theory in 3+1 dimensions where both the electric charge and both these guys are fermions. Exactly. And so then I can tell you later how we proved it. It's complicated. It's it's correct but complicated. And I don't know if this W2, W3 is simpler. If you know what those things mean, maybe it's simpler. But if I don't know what W3 really means, so it's not clear to me that has simplified it, but it endorses it. Okay, so in seeking other phases of such insulators, we know that if there's some other phase where the monopole is E/2, meaning theta is pi, we can combine it with the known topological band insulator to produce a phase where theta is 0. So it's enough to classify phase with theta equals 0, right? Which means that it's enough to restrict to monopoles which are electrically neutral and which are bosons. So then we can refine the question. Say that spin orbit coupled insulators, the bulk gap, no exotic excitations, and the monopole is an electrically neutral boson, and there's the ordinary band insulator, or there are other examples. Okay? And the only thing we know really is about the monopole. So let's try to use the monopole. Right? So we do the same kind of thing where we throw in a monopole from the vacuum into the bulk insulator, and we know that whatever it leaves behind must have the same properties as whatever it became, the monopole became, once it went into the medium. The vortices are bosonic, but what vortex, because the monopole carries H over E magnetic flux, and the basic superconducting vortex in an electronic system has H over 2E flux. This tells you something about H over E vortices. So 4 pi vortices in the Cooper pair phase are constrained if the surface is a superconductor, right? So but we have learned something concrete about the surface by understanding something about the bulk monopoles. And then we use that, and it turns out that this is enough to show that there's nothing non-trivial in the charge sector of the theory. So in particular, we can condense these, because these vortices are bosons and they are totally trivial, they don't carry any fractional charge, nothing totally trivial, we can condense them. Just like I did in the bosonic topological insulator, I condensed paired vortices and got something, a topologically ordered state. I can do the same here and get a topologically ordered state, which preserves all the symmetries. And it's easy then to show that the only possible anomaly that can exist in the theory comes from the neutral sector of the theory. Right? There's no anomaly associated with the charge U1. So anything non-trivial is an SPT phase that's protected purely by time reversal and not by the full U1 semi-direct time reversal, which means that I can construct it as an electronic Morton insulator, and the spins form a topological paramagnet that's protected by time reversal. Okay? So it's a purely time reversal protected SPT. And that's a problem that we had solved before. There's precisely 3 such phases. There's Z2 squared classification of such phases, and then that's it. So that combines with the Z2 where theta is pi, and that gives you Z2 cubed. Anyway, so that's the end. That's all I've prepared. I know, that's great. And with various diversions, it's great. You know, this